In our last class, we were talking about nodal analysis, and we introduced a wrinkle where you have a voltage source that is not grounded. Those floating voltage sources, as we call them, present a problem when you try to do the KCL equations at the nodes because you don't know the current through the voltage source. We then introduced the concept of a supernode and showed that it could solve the problem of not knowing that current. What we're going to do in today's lecture is formally develop the supernode analysis algorithm. We're going to do a couple examples, and then we're going to switch gears a little bit and introduce another type of analysis technique called mesh analysis. But let's start with the supernode analysis algorithm. So once again, these are for type 2 circuits. These are circuits that have floating voltage sources. You're going to see that many of the steps in this algorithm are identical to the type 1 circuits, but there are a couple additional steps as well. So the first step is always the same. You always have to have a reference node. In nodal analysis, you must have a ground or reference node. In some circuits, ground will be predetermined. In other circuits, you will have to define that yourself. Obviously, if you're given the choice to define where ground is, you want to put it where the maximum number of voltage sources are grounded. The second step is you look at every node and determine whether you know the voltage at that node or not. So basically you look at every node, and if you see that there's a connected voltage source to that node, you then have to determine, is that voltage source grounded or not? If the voltage source is grounded or connected to another voltage source connected to ground, then you know the voltage at that node. That's what we did before. If you have a voltage source and it is not grounded, in other words, it is floating, you determine the supernode associated with that floating voltage source. And if it's a floating voltage source and you have a supernode, you have to assign a variable to the node at either end of that supernode. Then, if you have a node that has no voltage source at all, you also do not know the voltage, so you assign a variable to it. So if there's no voltage source at all, you have to assign a variable. Once you assign your variables to all of your nodes, you now write the equations. The first thing you do is, if you have dependent sources, you express the control variable in terms of the node voltages. We did that before in an example in last class. You do that again here. Second thing you do is you start writing your KCL equations. If you have a regular node that doesn't have a supernode attached to it and there's an unknown voltage at that node, you write a KCL equation for that node. Then for every supernode, you write a KCL equation. Finally, for every supernode, you also write a source equation. You're going to end up with n equations and n unknowns. The n unknowns are these unknown node voltages, V1, V2, V3, etc. So you compile the equations, and then you solve it. And then, if necessary, if you're asked to find something other than the voltage at every node, for example, maybe you're asked to find a current through a resistor, or you're asked to find a power, or you're asked to find the current through a voltage source, then and only then you use Ohm's law of necessary to find the current through the resistor, or you use KCL to determine the current through a voltage source of interest. Notice that until this point, we did not do any KCL equations where we needed to find the current through the voltage source. This is what we do now if necessary. We do this once we know all the voltages. So if you look at this algorithm, the steps that are new, this 2a part 2, where you have these supernodes that you identify, that's a new step that we didn't have before. Likewise, in step 3, 3c, the KCL equation we write for the supernode is a new step. And then the source equation we write for each supernode is a new step. The rest of the steps are identical to what we had before. So let's start with an example. This is the same circuit that we tried to attempt a couple pages ago. So if you remember, we tried to attempt this back here, and we came into this problem where we did not know the current into that 2-volt source, and so we could not write a KCL equation at VB, and we could not write a KCL equation at VC. But now we're going to see that using the supernode idea, we can do this. So the first step is you have to look at every node and determine, do you know its voltage? If so, write it down. If not, write a variable. So we're going to start by assigning ground because there is no ground in the circuit. So there's nowhere that we can put ground where every single voltage source is grounded. You can either ground the 4-volt source or the 6-volt source or the 2-volt source, but you cannot ground all of them. We're going to put ground right here. This is going to be our ground node down here. So of course we know the voltage there already, it's 0 volts. Now let's look at every other node and determine, do you know the voltage or not? This node here, because it's connected to a 4-volt source that's connected to ground, we know the voltage, it is -4 volts. This node on the left here, it's connected to a 6-volt source, which is connected to the 4-volt source, so we know the voltage at the green node as well, it's +2 volts. This node on the top of the circuit is not connected to a voltage source at all. We do not know its voltage, so we have to assign a variable. We'll call that VA. This node here, it's connected to a voltage source. However, because of where we put ground, this voltage source is not grounded. We do not know the voltage at this node. We'll give it a variable, VB. And finally, this node here, once again, it's connected to the 2-volt source, but because the 2-volt source is not grounded, we do not know the voltage at this node. This is VC. So we've defined our variables. Once again, this is exactly what we did before. What we're going to do different now is we're going to recognize that this floating voltage source here, this 2-volt source, needs to have a supernode. And we're going to see that using the supernode idea will allow us to now progress and solve this circuit. Okay, now we can start writing our equations. Because we don't have any dependent sources, we don't have to worry about any control variables. So we can start writing our KCL equations. So we have a KCL equation at the VA node. We did this before. It's this current plus this current plus this current plus this current is equal to 0. So the current to the left is VA minus 2 volts over 2 kilo ohms. That's that current. The current through the next 2 kilo ohm resistor is what? VA minus -4 volts over 2 kilo ohms. The current through the next resistor is VA minus VB over 1 kilo ohm. And finally, this last current is VA minus VC over 1 kilo ohm. All of that equals 0. We simplify the circuit, we get 6 times VA minus 2 times VB minus 2 times VC equals -2. Second equation we write now is a KCL equation for the supernode. This is the step we did not do before. So you look at the supernode on the right here, we're going to sum up that current plus that current plus that current plus that current is equal to 0. Notice we're avoiding having to write an equation for the current through that voltage source. So the KCL at the supernode is what? This current is VB minus VA over 1,000. This current going down here is VB minus 0 over 1,000. This current is VC minus VA over 1,000. And notice once again, because we're going up rather than down, it's the voltage at the coming from point VC minus the voltage at the going to point VA over 1,000. So in the equation above, it was VA minus VC over 1,000. Here it's VC minus VA over 1,000 because we're going up rather than down. And then final current is VC minus 0 over 1,000 is equal to 0. Simplify that, we get minus 2 VA plus 2 times VB plus 2 times VC is equal to 0. So at this point, we've exhausted all of the KCL equations we can write. We don't write KCL equations at the green node or the pink node or the yellow node because there are voltage sources attached to them. And we had already did the VA node and the supernode. But we have 3 unknowns. We have 2 equations, 3 unknowns. Where do we get our third equation from? Our source equation. Remember, whenever you have a supernode, you always have a source equation associated with it. So the source equation, basically we take into account the fact that the 2-volt source connects nodes VB and VC. Specifically, what do we have? We have that VB minus VC is 2 volts, or alternatively, VB is equal to VC plus 2 volts. So at this point, we now have 3 equations and 3 unknowns. Equation here, equation here, equation here. 3 equations and 3 unknowns we can solve. I'm not going to go through the math here. You could use techniques from Math 220. You could use online programs to solve simultaneous equations, or you can do it manually. That's not my concern. My concern is the result. VA is negative 0.5 volts. VB is 3/4 of a volt. And VC is negative 1.25 volts. So at this point, we've now found the voltage at every node in the circuit. The problem did not ask us to find the voltage at every node in the circuit, however. The question asked us to find this current, Ix, this current up here. But now that you know all the voltages, we can now use Ohm's law to find Ix. Ix is the current through that top left 2 kilo ohm resistor. Remember, the current through the resistor is what? The voltage at the coming from point minus the voltage at the going to point divided by the resistance. So the voltage at this point is 2 volts minus the voltage at this point is negative 0.5 volts. Got to be careful about that double negative there, divided by the resistance. 2000 ohms. You work out the math, you get 1.25 milliamps, which is our final answer. So using the Supernode algorithm, we were able to solve this circuit even though we had this floating voltage source. Let's do one more example. This example is going to be a little more complicated because it's going to have dependent sources in there. So the first thing we do is we identify ground. Ground is actually determined for us. So we know that the voltage at this node is going to be 0 volts. The next thing you want to do is we want to assign a voltage or voltage variable to every node. So let's look at every node. We have a node here. Do we know the voltage at that node? We actually do. That node is connected to a 10-volt source. 10-volt source is grounded, so we know the voltage at this point is 10 volts. Then we look at this node. Do we know the voltage at this node? Well, it's connected to a voltage source. It's a dependent source, but nevertheless it is a voltage source. However, that voltage source is not grounded, so we need to assign a variable to this node. I'm going to call it V1. Look at this node. Do we know the voltage at that node? Once again, it's connected to a voltage source, a dependent voltage source, but it's floating, so we do not know the voltage here, so we will write a variable, V2. Then this is our last node. Do we know the voltage at this node? Once again, there's no voltage source at all connected to this node, so this is also a variable. So we call it V3. So at this point, we've defined all of our variables. When we go to solve this circuit then, the only variables we want to use in our equations are V1, V2, and V3. We do not want to introduce any more variables. So the next step is to look at our dependent sources and get rid of the controlling variables. So we have 2 dependent sources. We have a current-controlled current source here, and the controlling variable is this current IB. So we want to get rid of IB. We also have this current-controlled voltage source, 0.5 IA, where IA is the current through this 1 ohm resistor here. So the next step is to get rid of IA and IB. So we call these our control equations. We want to express both IA and IB in terms of V1, V2, and V3. So let's look at IA first. You could use Ohm's law. The current through this 1 ohm resistor here is what? IA is equal to what? The voltage at the coming from point minus the voltage at the going to point divided by the resistance. So IA is just V2 minus V3. Now let's look at IB. IB is a current through this 10-volt source. That's not going to do us any good, but because this 10-volt source is in series with this 2 ohm resistor, and we do know how to find the current through a resistor. We can do that. So IB is a current through the 2 ohm resistor. So it's what? It's the voltage at the coming from point, 10 volts, minus the voltage at the going to point, V1, divided by the resistance, 2 ohms. So we're going to see that these control equations will be substituted into our KCL equations when we write them next. First off, we have a supernode. Because we have a voltage source here, the fact it's a dependent source doesn't change the fact that it is a voltage source and it's floating. So we have a floating source here. Because we have a floating source, we need to do a supernode. So let's do a dashed red supernode around it. So the equations we're going to write is we're going to write a KCL equation at the V3 node. We're going to write a KCL equation for the supernode, and then we're going to write a source equation. So let's do our supernode KCL equation first. So we're basically going to say that this current plus that current plus that current plus that current plus that current is equal to 0. So look at the different points where current leaves that supernode. We're going to add those up to get our first equation. So this current going down is the current through this 2 ohm resistor. In that direction, it's a voltage at the coming from point that's V1 minus 10 over 2 ohms. Current in this direction is 3IB. So we get plus 3 times IB, but remember we do not want to have an IB variable, so instead we're going to substitute that using that expression there. IB is 10 minus V1 over 2. That is IB. This current is what? It's V2 minus V1 over 2. This current is what? It's V1 minus V2 over 2. And notice they cancel each other out. So if you recognize that, you can actually avoid writing those two terms completely. Finally, this current here is the voltage at the coming from point V2 minus the voltage at the going to point V3 divided by the resistance, plus V2 minus V3 over 1 ohm. And the sum of all of those currents is equal to 0. That simplifies to minus V1 plus V2 minus V3 is equal to negative 10. We set that aside. We then write a KCL equation at the V3 node. And this is just a standard KCL equation. It's not a supernode, so it's that current plus that current plus that current is equal to 0. Current to the left is what? V3 minus V2 over 1. Current going down is V3 minus 0 over 4. Current going to the right, it's a current source. It's 6 amps into that node, so the current leaving that is negative 6 amps. So it's minus 6 is equal to 0. You simplify this equation. This becomes minus V2 plus 5/4 times V3 is equal to 6. The next step is we need to write our source equation. So we have this source up here. The fact it's a dependent source doesn't change the fact that it's a source equation. So what this is telling us is the node to the right, which is V2, is 0.5 IA volts greater than the node at the left, which is V1. So we end up getting from our source equation, what? We get V2 minus V1 is 0.5 times IA, but IA is what? IA was V2 minus V3 over 1. So this becomes 0.5 times V2 minus V3. This equation then simplifies to 2V1 minus V2 minus V3 is equal to 0. So at this point we have 3 equations and 3 unknowns. We have this equation we got from the supernode KCl. We have this equation that we got from the node 3 KCl. And we have this equation that we got from the source equation. So now that we have the 3 equations and 3 unknowns, we can now solve for them. I'm going to set up the matrix equation. For those of you who did not have Math 220 yet, don't worry about it. There are other ways you can solve this as well. But from the coefficients of the 3 equations, we get the following matrix. -1, 1, -1, 0, -1, 5/4, 2, -1, -1, times a voltage vector V1, V2, V3. Right-hand side is -10, 6, and 0. Where does this come from? Once again, it comes from these coefficients. For example, this third equation, we have 2, -1, -1, 0. 2, -1, -1, 0. Likewise, here we have -1, 5/4, 6. And notice V1 has no term, so it's 0, -1, 5/4, 6. 0, -1, 5/4, 6. And the first equation was -1, +1, -1 equal -10. -1, +1, -1 equal -10. Using either Math 220 techniques or using some online program to solve simultaneous equations, or doing it by hand, which can be sort of tough for 3x3 systems of equations, you can now solve, and you get that V1 is 6 volts, V2 is 4 volts, and V3 is 8 volts. Now in this problem, we were asked to determine the voltage at every node. At this point, we've done that. V1 was 6 volts, V2 was 4 volts, V3 was 8 volts, so we are now done with this problem. Had we been asked to find something else, for example, had we been asked to find the power delivered by the 10-volt source, we would now use these V1, V2, V3s to solve for IB using this equation here. Once you knew IB, which is the current through the 10-volt source, you could then find the power absorbed or delivered by the 10-volt source. So the bottom line is, once you know all the node voltages, you could then use things like Ohm's law and KCl to find anything else you're looking for in that circuit. We're going to switch gears now a little bit and talk about another type of analysis called mesh or loop analysis. It is sort of the dual of nodal analysis in the sense that it does everything the opposite way. In nodal analysis, we had voltage variables, but we use Kirchhoff's current law. In mesh analysis, we're going to have current variables, but we're going to use Kirchhoff's voltage law. If you think back to the very beginning of this note packet, we talked about the differences between a single loop circuit and a single node pair circuit. A single node pair circuit was sort of like nodal analysis. A single loop circuit is sort of like a simplified version of mesh or loop analysis. So like nodal analysis, it's a very systematic approach, but now we're going to use KVL instead of KCl, and we're going to have current variables rather than voltage variables. In circuit analysis, there is a general technique called loop analysis, and there's a subset of that called mesh analysis that we're going to be using here. I'm not going to talk about more general loop analysis. We're talking specifically about mesh analysis. Mesh analysis is limited to circuits that are called planar circuits. A planar circuit is a circuit that basically could be drawn on a sheet of paper without coming out of the paper at all. Loop analysis of planar circuits is called mesh analysis, which is the technique we are going to be covering here. So let me explain a little bit more about planar circuits. So first off, let me specify. On this page here, when I have a connection like this, basically this is a connection. When I draw something like this, you can sort of think of it as this: no connection. So looking down below here, this first thing here is a planar network. It can be drawn flat. You don't have to have anything like this where you have one wire looping over the other one. If you look at the second circuit here, you first look at it and you see that point there and you say, wait a minute, there's no connection there that's going to be non-planar. However, if you take this wire here and move it out to there, likewise, if you take this wire here and move it into here, you get the following. The wire you moved out goes there, the wire you move in goes there, and the rest of these wires are where they were before. So notice the second circuit, even though it looks like it's non-planar because of this, it can be redrawn flat, so it is also a planar circuit. This third one, on the other hand, there's nothing you can do to get rid of that thing there. There's no way you can stretch these wires to get rid of the fact that they cross over without connecting. So this one could not be drawn flat on a piece of paper. So this is a non-planar circuit, so this technique that we're covering here does not work. So before we get into mesh analysis, we do need to define a few terms. Let's do that here. So first off, let me draw a little circuit here without any circuit elements. Let's say that we have nodes here and assume that there are circuit elements between every node here. So a loop is any complete path that does not intersect itself. So for example, that is a loop. That is a loop. That is a loop. That is a loop. All of those are loops. This is not a loop because it crosses over itself. So that's what a loop is. The perimeter is the outermost loop. So there are lots of loops in a circuit, but there's only one perimeter. Basically, the outermost loop. That's the perimeter. A mesh is a loop that does not contain any other loops within it. I like to think of these as window panes. So these are our window panes. So a mesh, that's a mesh, that's a mesh, that's a mesh, that's a mesh. So there are 4 meshes in this particular circuit. So a mesh current is defined to be a current that flows along a mesh. So if you have a mesh here, a mesh current would be this current, this loop current, or we call it a mesh current through there. So there's a mesh current there. There's a mesh current for this mesh. There's a mesh current for this mesh, and a mesh current for that mesh. So those are what we call mesh currents. Next term is a branch. So a branch is any connection between nodes. So that's a branch. That's a branch, that's a branch, that's a branch, that's a branch, etc., etc. So basically, think of branches as where our components are going to be. So an interior branch is a branch that's not on the perimeter. So an interior branch, that's an interior branch, that's an interior branch, that's an interior branch, that's an interior branch. This is not an interior branch because it's on a perimeter. Notice, and this is important, that every interior branch is the border between 2 meshes. So that interior branch, there's a mesh here, and there's a mesh here. That interior branch is the border between exactly 2 meshes. So every interior branch is a border between exactly 2 meshes. That's an important point. Next important point, if you have a perimeter branch, for example here, this is a perimeter branch, the branch current, which is the physical current through that circuit element, is going to be algebraically the same as the mesh current. So if you have a mesh here, whatever that mesh current is, suppose it was 2 amps, that means that the physical current through this branch is also 2 amps. So the mesh currents are the same as the perimeter branch currents. But what about these interior branches? So if you think about this branch here, which borders 2 meshes, its physical current is going to be the algebraic sum of the mesh currents for the 2 meshes adjacent to that branch. So for example, This mesh has a current like that. This mesh, we'll do it in another color, has a current like that. The physical current through this branch here in the middle, the physical current through there is the algebraic sum of the red current and the blue current. And we'll see this in our algorithm in a couple pages. One other final point here, if you define all of your mesh currents in a clockwise way, then these branch currents are always going to be the difference between two meshes. Because notice, if all of your mesh currents are clockwise, such as in this example here, the branch current is going to be in the same direction as one of the meshes, the opposite direction of the other mesh. So let's look at this in a little bit more detail, make sure we really understand these different definitions. So here we have a circuit here, and I have my different nodes labeled A, B, C, D, E, F, G, and H. So we want to find all the different things. So the perimeter is basically the border of the circuit. So it's going to be A to B to C to D to E to F to G. So that's our perimeter. We have three different meshes, three different window panes. So the first mesh is going to be between A to B, B to C, C to H, H to G, back to A. And we're going to define that mesh current as I1. And I'm going to make it a clockwise variable. Mesh 2 is going to be between C to D, D to E, E to H, H to C, and we're going to define its current as I2. So imagine this current that's swirling through this mesh. Then finally, the third mesh, mesh 3, goes between G and H, HE, E and F, F to G, and we're going to call its variable current I3. So these mesh currents are going to be the variables that we're going to be using. Our interior branches, there are three of them. So we have a branch between G and H, so that's this branch here. We have a branch between H and E, that's this branch here, and a branch between H and C, that's that branch right there. So how do the branch currents relate to the mesh currents? Remember, the mesh currents are the variables we're going to be using. The branch currents are the physical currents in the circuit. So let's look at IAB. IAB is a branch current. It's a current through this branch of the circuit. Because it is a perimeter branch, IAB is the same as the mesh that it's connected to. So it's the I1. So IAB is equal to I1. Notice I1 is clockwise, and so it goes in this direction, which is the same orientation as IAB. So IAB is just equal to I1. Let's look at ICB. ICB is also a branch current, so it's also going to be equal to a mesh current. However, because ICB is going in this direction and I1 is defined as clockwise, notice they're opposite directions. So ICB is negative I1. So the branch currents are equal to the mesh currents, but there could be a difference in sign. IHC is an interior branch current. Interior branch currents are always an algebraic sum of mesh currents. So if you think of IHC, you have two different currents contributing to that. You have this I1 mesh current here, and you have this I2 mesh current there. Those two together contribute to IHC. IHC goes from left to right. It's defined as left to right. Notice that is the same direction of I2, but it's the opposite direction of I1. So IHC is I2 minus I1. This goes back to what I said before here. Each interior branch forms a border between exactly two meshes, and if all meshes are defined in the same direction, clockwise or counterclockwise, then the branch current is the difference of the two mesh currents. That's exactly what we see here. IHC is I2 minus I1. IHG is this branch current here. Once again, that is the branch that borders mesh 1 and mesh 3. So IHG is going to be a combination of I1 and I3, but it's in the same direction as I1, the opposite direction as I3. So IHG is equal to I1 minus I3. I did not do this last one, IHE. Let me define it here. IHE is that current there. So what would it be? It is between meshes 3 and 2. IHE is going from top to bottom. That is the same direction as I3, the opposite direction of I2. So IHE is equal to I3 minus I2. So once again, if you define all of your mesh current variables as clockwise, when you get these interior branch currents, it's always going to be one current minus another one current minus another one current minus another one. Anyway, it's extremely important that you understand the distinct difference between mesh currents and branch currents, because you're going to need that understanding in order to do this algorithm. So let's get to the algorithm. If you remember, in nodal analysis, we had two different types of circuits. Type 1 were circuits where if there were voltage sources, they were all connected to ground or connected to other voltage sources connected to ground. And then type 2 were ones with floating voltage sources. In mesh analysis, we also have type 1 and type 2 circuits, except it's different. A type 1 circuit in this case is a circuit where if you have current sources, they have to be on the perimeter only. They cannot be in an interior branch. We're not saying that you have to have current sources to do mesh analysis, but what we're saying is that if you have current sources, they have to be on the perimeter only. How about the voltage sources? They can be anywhere. So in nodal analysis, it's the location of the voltage sources that determines which algorithm you use. In mesh analysis, it is the location of the current sources that determines which algorithm you need to use. So what are the steps? The first step is you redraw the circuit if necessary to make sure that no meshes overlap. This goes back to what I showed a couple pages ago with these planar circuits. Mesh analysis only works on planar circuits, so if you have an example like this one here that looks like it's non-planar, you need to redraw it to make it planar. This is a step that we will rarely have to do, so you really don't have to worry about this for the most part. The next step is to look at every mesh and determine whether you know its current by seeing whether there is a perimeter current source. If there is a perimeter current source for that mesh, then the mesh current is known and you can write it down. 3 milliamps, 5 milliamps, negative 2 milliamps, etc. If there is no perimeter current source, then the mesh current is unknown and you assign a variable, I1, I2, I3. These are going to be the variables that we're going to be using in our equations. So these are what we use in our equations. So once you examine every mesh and determine whether you know the current or not, you now write the equations. First off, if there's a dependent source, you express the controlling variable in terms of these mesh currents. So if dependent sources exist, control variables in terms of the mesh currents. This is similar to what we did in nodal analysis. If you had a dependent source, you wrote the controlling variable in terms of the node voltages. Now we're writing the controlling variables, whatever they are, in terms of the mesh currents. The other equations you write then is you write a KVL equation for every mesh without a current source. In other words, these unknown meshes, you write a KVL equation. And the key thing here is the voltage across a resistor. So for example, if you have a resistor here, let's call it R sub K, the voltage across a resistor is going to be what? It's going to be the value of the resistance times the branch current. But what's the branch current going to be? What's going to depend upon these meshes. So for example, if this had mesh variable I1 and this had mesh variable I2, the current through that resistor going from left to right was I1 minus I2, so the voltage would be R sub K times I1 minus I2. So notice the voltage across the resistor you could write in terms of the resistance and the branch current, and the branch current in turn you write in terms of the mesh currents. And we're going to see that this is an important part of this algorithm. So you write a KVL equation for each mesh without a current source. If you have 3 unknowns, you're going to end up with 3 equations. 5 unknowns, you're going to end up with 5 equations. So you compile the equations and you solve to get your mesh currents. Once you have the mesh currents, depending upon what you're looking for, you can now find voltages across resistors by using Ohm's law. That's step 6. Or if you want to find the voltage across a current source, you apply KVL for that loop at this point. So steps 6 and 7 are steps that you don't always need. So this is if needed. We'll see this in some of the problems we do. So once you find the mesh current, if necessary, you write additional equations. Step 7 in particular is a key step here. We do not do a KVL equation for any mesh involving a current source when we're solving for the currents, because we don't know what the voltage across the current source is. The only time you ever write a KVL equation for a mesh involving a current source is this step 7, and you do this after you find the mesh currents. That's the only time you ever write a KVL equation for a mesh involving a current source. Let's do one example. We're asked to use mesh analysis to find the power supplied by each of the sources. You might recognize this circuit. We did this circuit earlier using nodal analysis. Now we'll do it using mesh analysis. So the first step is to identify our meshes. We have a mesh here. We have a mesh here. And we have a mesh here. 3 meshes. Then you look at every mesh and you determine whether you know the current through it. If you know the current, you write it down. If you don't know the current, you assign a variable. So this pink mesh has a perimeter current source. It's 1 amp and it's going from bottom to top. And so the current through this mesh is 1 amp. This means that the current through the 1 amp source is 1 amp, obviously. This does not mean that the current through that 4 ohm resistor is 1 amp, because a 4 ohm resistor is a combination of 2 meshes. So the physical current through the 4 ohm resistor is not just 1 amp, it's 1 amp plus whatever is through the yellow mesh. Likewise, the current through the 10 volt source is not just 1 amp, it's going to be 1 amp plus whatever the current is through the green mesh. So looking at the yellow mesh then, there's no current source at all, so we do not know what that current is. We're going to assign a variable. I always like to use clockwise variables. So I'm going to call it I1. The green mesh, once again, has no current source at all. We do not know the current through that mesh, so we're going to assign it a variable. Once again, I like to make it a clockwise variable. We'll call it I2. So we assign our mesh currents. So the next step is we write KVL equations for what? Mesh 1 and mesh 2. So let's do mesh 1 first. So we're going to start at this point here, and we're going to sum voltage drops across all the elements as we go through that mesh. So once again, I want to mention when you have a resistor, the voltage across a resistor you get from Ohm's law, it's the resistance times the current through that. So this 2 ohm resistor has current I1 going from left to right, so the voltage across it is going to be what? 2 times I1. 10 ohm resistor is a little bit trickier. It has 2 different currents flowing through it, I1 and I2. I1 going right to left, I2 going left to right. So the voltage across the 10 ohm resistor is going to be what? Let's put the plus here and the minus here arbitrarily. It's going to be 10. In this direction, with going from right to left, it's going to be 10 times I1 minus I2. Notice that if we put the plus on the left rather than on the right, it's 10. The current now would be I2 minus I1. So notice which current you put first depends upon where you put the plus and where you put the minus in the voltage. If you put the plus on the left and the minus on the right, you're going from left to right, so it's I2 minus I1. If you put the plus on the right, it's going to be I1 minus I2. All right, so now we're ready to do our KVL equation. So the voltage drop across the 2 ohm resistor is 2 times I1, plus the voltage drop across the 10 ohm resistor is going to be plus 10 times I1 minus I2. Notice if we use this instead, it would be minus 10 times I2 minus I1. It's the same term either way. So as long as you're consistent, that's fine. The voltage drop across the 4 ohm resistor is going to be the resistance times the current in the direction we're going. We're going from right to left through that 4 ohm resistor. In that direction, that current is I1 going in this direction, but then we also have 1 amp going in that direction. So the net current is 4 times I1 minus 1. So 2I1 plus 10 I1 minus I2 plus 4 I1 minus 1, all of that equals 0. We can simplify this equation. We get 16 times I1 minus 10 times I2 equals 4. Now let's do KVL for mesh 2. So I'm going to start down here. I'm going to go clockwise. I'm going to sum voltage drops. So we first go through what? We go through a 10 volt source. We get minus 10 volts plus 10 I2 minus I1 plus 2.5 times I2 is equal to 0. So writing that down, we get minus 10 volts plus the voltage drop going from left to right across the 10 ohm resistor is 10. Since we're going left to right, it's I2 minus I1 plus 2.5 times I2 is equal to 0. We simplify that. Minus 10 I1 plus 12.5 times I2 is equal to 10. Two equations and two unknowns. We could set up our matrix if we want. 16 minus 10 minus 10, 12.5 times our current vector, I1, I2 is equal to 4, 10. Solving this, we get I1 is equal to 1.5 amps, I2 is equal to 2 amps. At this point, we have now found all of the mesh currents, but we have not solved the problem yet, because the problem did not say, find all the mesh currents. The problem said, find the power supplied by each of the sources. So at this point, we can now use these mesh currents to solve the rest of the circuit. So to find the power absorbed or supplied by the 1 amp source, you need to know the voltage across it. So if you notice, this pink mesh we have not touched yet as far as doing a KVL equation. And that's because we didn't know the voltage across the 1 amp source. So we couldn't use that to find that current, and plus we knew the current anyway. We knew it was 1 amp. But now that we know all of our currents, we can now do KVL for that bottom left mesh. So what we do is we assign a voltage variable. Let's call it VS. I'm going to arbitrarily put the plus on top and the minus on the bottom. And I'm going to do KVL for the pink mesh. This is a step 7. This is a step 7 that I talked about in this algorithm here. Because we want to find the voltage across that current source, we can apply KVL now once we know all the currents. So what do we have? Starting from this bottom left point here, we get minus VS, that's our unknown now, plus the voltage drop across the 4 ohm resistor is 4 times the current going from left to right is going to be 1 minus I1, but we know what I1 is now. I1 is what? 1.5 amps. So we know that now. And then the voltage drop across the 10 volt source is 10 volts plus 10 is equal to 0. So we get minus VS plus 4 times 1 minus I1 plus 10 is equal to 0. There's only one unknown, VS. We solve for VS. You get VS is equal to 8 volts. Once you know VS, we can now find the power associated with that source. We know that we have 8 volts across it, and we know that we have 1 amp going through it. And notice the current enters the minus terminal, so the absorbed power is going to be minus 8 volts times 1 amp, or minus 8 watts. So this source supplies 8 watts of power. And if you compare this to the nodal analysis problem where we did the same circuit, we got the same answer. For the voltage source, the power is a little bit easier. So for the voltage source, We have a 10 volt source here. We know that there are 2 mesh currents associated with it. I2 mesh is going in this direction, it's 2 amps. And then the pink mesh on the left has a 1 amp going clockwise, so it's going down through that. So the net current, the physical current going through that voltage source is what? It's 1 amp going up. So the branch current is 1 amp going up. There are 2 mesh currents, 1 amp going down from the left mesh, 2 amps going up from the right mesh, but the branch current, which is the algebraic sum of the 2 of them, is 1 amp going up. So the absorbed power is what? The voltage across the voltage source is 10 volts. The current is 1 amp. Since the current, the physical current, hits the minus terminal first, the current is going in that direction of 1 amp, we put a minus. So it's minus 10 watts absorbed. So this also supplies power. This supplies 10 watts of power. So those are our final answers. If you compare it to nodal analysis, we got the same answer using a completely different approach. So this ends this lecture. Next class, we will continue with mesh analysis. We'll look at more complicated circuits, and then we'll finish up by comparing mesh analysis and nodal analysis and see which one is easier in which situation. Have a good day.